Hi, my name is Emily Chang. I'm the Design Technology Manager of HOK, Asia Pacific. My BIM talk today is Interoperability and Beyond. Let's get started. If we look up the definition of interoperability, we will find it has two layers of meanings. The first meaning is the ability of groups to operate in conjunction with each other. The second meaning is the ability of computer systems or softwares to exchange and make use of information. This term has three folds, which includes people, computer systems, and software. So, how does these three connect in the BIM workflow? Let's zoom in and take a look at a typical size BIM team in one of our HOK projects. As I mentioned earlier, the first definition of interoperability, the ability of groups to operate in conjunction with each other. The BIM team that includes owner, general contractor, architects, engineers, and subcontractors. Each role has their own responsibilities. It is the ability of these groups be able to use the tools, which enabling them to communicate and coordinate in conjunction within the BIM team and bringing the projects into reality. Obviously, communication is required for all of the collaboration's needs. The more dispersed teams are, the more important efficient communication becomes. The work sharing enables teams to understand design changes no matter where they are. Therefore, bandwidth or latency of the internet connection needs to be included in the considerations when setting up the team. We also learned how to select hardware for 3D and BIM workstations running different software. Realizing that one hardware specification does not fit all users' needs. Our information technology team had to reevaluate our BIM users' specific computing requirements based on the software usage. With the recent software as a service, SaaS, will become more common for software application being hosted over the internet via a subscription model. Our internet dependence will only become a greater requirement in order for BIM teams to work smoothly. When the design and construction team utilize different tools during their design process, be able to connect the primary software among different disciplines, interoperability workflows is even more essential. If we talked about the second definition of interoperability, we need to zoom out to a big picture that consists of software, computational design plugins, applications, cloud computing platforms that are so intertwined. You will need a very large map in order to navigate through this maze of information exchange ecosystem. Learning how to connect one tool to another and make use of the information is not always easy. It requires innovation, creativity, and most importantly, a multidisciplinary mindset. The BIM use of connecting the information exchange ecosystems are both width and depth. The quality of everything is being connected is aligned with Leonardo da Vinci's philosophy of interconnectedness back in the 16th century. He saw science, engineers, and arts as complementary rather than distinct disciplines, and thought that ideas and formulates in one realm would inform the other. The project and team I've been referring to is the Anaheim Regional Transportation Intermodal Center, also known as ARTIC. Located in the home of Disneyland, Southern California in the US, the city wanted an iconic structure for its new transit hub to celebrate mobility and fantasy, inspired by great transit halls of the of the past, as well as the historic hangars found throughout Southern California, Arctic takes its form from a rotated catenary arch. Designed by the Los Angeles office of HOK, the 6,200 square meters building opened in 2014 with an ethylene terafluoroethylene ETFE cladding around a steel shell. The exuberance design is a class by itself. The Arctic now serves passengers of the region's Amtrak and Metrolink trains, as well as the local and regional bus lines. It will also accommodate future high-speed rail through California. The complexity and scale of the design and execution requires very diverse skill sets. Achieving the project goals within budget was one of the many challenges that became achievement of a large group of designers and technical experts. For architects, the use of BIM was crucial in clearly communicating this iconic design to the clients, the public, and in assisting the project team in developing the complex form, geometry, and functions into reality. BIM also delivered coordinated documents in a compressed timeline, maintaining design intent well into construction. The greatest benefit of BIM utilization on the Arctic project is the coordination efficiency achieved during design and construction. The design team utilized Revit, Rhino, and CATIA as the primary software, along with Navisworks for pre-construction clash detection. The structural engineer and the enclosure consultants used proprietary tools to generate geometry in multiple formats suitable for their purpose and information exchange. Multiple analytical tools were used to study the various components and elements types. Entire structure systems were modeled to ensure holistic fidelity with integrated systems. In the general contractor's statements, the BIM model was credited as being very significant not only to them, but also to subcontractors as well. The iconic design had requirements that could not be built without the BIM analysis and models. Due to the complexity of the project, utilizing geogrid dimensions, it could have been impossible to coordinate location without BIM. By using BIM, the project team was able to produce 3D printed study models, but was also able to analyze the pedestrians and vehicular traffic to ensure safe path of travel. Analytical BIM models were employed for performance simulations of wind, ventilation, comfort, energy, temperature, daylighting, and shade. The analysis also useful to confirm the sustainable strategies to achieve LEED Platinum certification. For design control and interoperability, all components associated with the complex shell form were coded into what has become known as the geogrid by the build team. The 3D design was reduced to the simplest geometric elements, points and arcs, to convey the exact design dimensions to all stakeholders while remaining software agnostic. The approach was carried through to confirm as-built survey. The fabrication of the structure steel was designed with complex compound curves. The only means to fabricate this material is by the use of a model. Once fabricated, the only means to erect within tolerance was by using the geo points. As the general contractor stated, the as-built model is the only way to accomplish this. Computer numeric control fabrication technology, CNC, was used for the three-way curved curtain wall at the north and south entrances. Because of the geometric data, defined points for the front of the glass, determining the armature connections and column location requires precise control of the positioning. Using BIM eases the production of the complex or three-dimensional shapes that are almost impossible to duplicate with manual machining. The integration of the facade structure and the arch structure were formed early in the competition phase. The ETFE pillows take complex forms to match the curves of the arches, forming the envelope. Each pillow is sized differently, consisting of 3 layers of ETFE. Although it's not the first project to use an ETFE cladding system in Southern California, the sleek, comfortable quality of the Great Hall interior has become a tourist attraction. The build team used BIM in their visual design and construction process. BIM is used not only for 3D coordination, fabrication, clash detection, construction sequencing, but also for as-built documentation. Let's watch a video about the fabrication and construction process of Arctic.
Arctic's distinctive shell is comprised of unique and sustainable materials. The diagrid steel, which creates the diamond pattern, was manufactured in Texas. Entirely new methods had to be developed in order to create the steel pieces for the shell, each of which was completely different in its dimensions. This innovative shell design effectively disperses forces from winds and earthquakes, ensuring the safety and longevity of the building. A seismic joint isolates the terminal structure from the connecting bridge, allowing the two structures to move independently during a seismic event. Perhaps the most eye-catching part of Arctic is the building skin, made of a material called ethylene tetrafluoroethylene, or commonly known as ETFE. Weighing just 1% as much as glass, ETFE has been used around the world for important projects like Fished Olympic Stadium in Sochi and the Olympic Water Cube in Beijing. The Arctic project has the largest ETFE application in the United States. The material works as a pillow system, waterproofing, shading, and insulating the building while still allowing sunlight to illuminate its interior. Rope access technicians scaled the diagrid steel framing in order to install the ETFE. After both the inner and outer layers had been applied, air pumps were used to inflate the pillows. The overall comfort of Arctic's visitors is very important. There are many eco-friendly provisions in place to ensure the proper temperature and amount of ventilation are obtained. Radiant floors heat and cool the necessary areas of the building without wasting energy on the spaces that are not occupied by visitors. Pipes carry hot or cold water underneath the floors, depending on the desired effect. In addition, a state-of-the-art louver system opens and closes the vents near Arctic's ceiling, providing the perfect amount of ventilation. This, along with the abundance of natural light, makes visitors feel as if they are outdoors when in reality they still have a roof over their heads.
Here's the owner's statements of Arctic. Using building information modeling for Arctic, a first for the city, allows the city to have detailed facility information as never before. Arctic serves as baseline for future benchmarking. During design, the integrated approach using BIM allowed the design team to share more information and produce an iconic design for a memorable and sophisticated structure, designed to tight tolerance and employing advanced material and systems. The detailed design information fed the cost estimates, bids came in well within budget tolerance. Although not traditional construction documents were produced during using BIM, the experience will inform future projects in recording design criteria and standards. In the 16th century, Da Vinci thought that ideas formulated in one realm would inform the other is still true. The BIM community will be the new breed of polymath who will be master of interoperability that will continue blending technology, sustainability, innovation, and comprehensive building knowledge with a multidisciplinary mindset and beyond. With that, I would like to end this talk with one last video. Thank you.